Hi, my name is Loris Crow, and we are executing a Showtime. Zig Showtime is the show where members of the Zig community come on stream to share coded ideas with the broader public. Every episode features two speakers who will present and take questions from you, the viewers. Zig Showtime, it's not just what you're seeing on the live stream, but also the discussions that you can have while watching. And that's why I encourage you to join one of the existing Zig communities that you can find by going to ziglang.org. So, episode 18. Hello, everyone. Thank you for being here. I know this is a bit, early of a show compared to what people in the United States, especially I guess West Coast, are used to. So thank you for who could make it. Let me go through some news then before we start with the talks. I guess for this week, there aren't many news except for, a couple of status updates. One, I guess, I can talk about what I'm doing with the website. So work is progressing, which is nice. I'm working on the Zig doc test tool, which is now being integrated with Hugo and everything else. So I'm getting to a point where, I think most of the design work is done with the website, but there is a big problem still with the tooling. Like if you want to contribute and you want to set up everything on your machine, right now it's not super trivial, but we are getting there. Once the integration with the new Zig doc test tool is going to be complete, it should be kind of easy to get up and running also on your machine, which is important because we want translations, right? So I'm also looking forward to be able to explain to everybody how the translation process work, and I hope to be able to engineer something that it's not too tedious. So personally, I'm happy with the progress that we have. I'm having there. A second news, which is more than a news, it's just a sneak peek. I'll repeat that also at the end of the show. So for today, I don't have yet the next Showtime set up completely. But what we are trying to do to see if it's possible for either next Showtime or the one after that, next Showtime or another Showtime in the future, is to see if we can have a short group Q&A about what's happening with Apple and Apple Silicon, which I think it's interesting. If you've been following on Twitter, there's been a lot of activity there. I guess Jacob first and foremost, but then also Frank, who is also going to speak now. There's a lot of people that have been trying to unpack what the hell is going on Apple Silicon consigning and everything else. So I hope to make this make some kind of show format that is not just a normal talk, but a bit more interactive, multiple people. We'll see what we can do once we get there. So I guess these were the main news. And another smaller news, I guess, is that I promised that I would publish a video on YouTube, like some content that is not just a live stream recording and then put on YouTube. And I published a video about some of my opinions about the website redesign that Rust had in 2018. So at the while I started the work for the redesign work for the ziglang.org website, I wanted to see what other programming languages were doing. And while looking at at the main programming languages, Rust stood out because apparently the new website, well, maybe it's not the new anymore. Again, it's from 2018, but there was this big website change for Rust, and a lot of people were unhappy with the product, with the new website. And I personally like the new website, and I dug around a little bit to see why people were so annoyed by the new design. And in the video, basically, I kind of recap this exploration and give some opinions on why I think things went the way they did. And I mean, it's all, I think it was interesting because these are all questions that are relevant for us. I mean, us as a community, and also me personally, I'm working on a new redesign. I don't want to be the guy that creates a redesign that everybody hates. So I wanted to know what I should make sure to get right and what to avoid. So that said, that's it for this week. So, well, anyway, you can find the video on YouTube. Like, just go to the Zig Showtime YouTube channel. You'll find it there. So I think we can move to the first talk. So let me bring up the title screen. Okay, so I don't think Frank needs an introduction. So I just want to thank him for his work with Zig and for contributing not just code, but also talks like this, and like his previous one on other crypto work that he did for the Zig standard library. So let's just give him the floor as fast as we can. The title is 25519. Yes, that's a short and enigmatic title. Frank, the stream is yours.
Hello, everyone, and welcome back. So, in the last episode, we mainly looked at symmetric cryptography, in which we had no key that was for hashing, or a single secret key used for encryption and authentication. So, if we want to encrypt something for someone, we do it with a secret key. And in order to decrypt it, the recipient has to use the same key. But how do you securely share that key to start with? This is something we didn't discuss. And anytime we connect to a website using TLS, our client is able to verify that it's talking to the right server. But at the same time, the client can't pretend to be that server, which is great. So we then use encryption, but we didn't agree on a key prior to the connection. So how does that work? This all relies on asymmetric algorithms. And with this, we can prove that we know something without revealing what that is. Or we can have two or more parties compute something together, but what each party had to compute remains secret. So probably the easiest and most classic example of that is a simple Diffie-Hellman key exchange. So in this example, we have, so I think on the left it's Zigli. I don't remember the name of the other guy, so whatever, I'm just going to call him his buddy.
He's zero.
So it's zero. So this is Ziggy and zero. Okay, perfect. So Ziggy and zero wants to share some secrets. How can they do that? They need a secret key first. So what they can do is pick up a random number. So Ziggy is gonna pick some X. It could be anything, just something random, unpredictable. And zero is gonna be doing the same thing, and it's gonna have Y. This is secret. But then they're gonna share G raised to the power of their secret. So G is something that's public. It's a number, but it doesn't have to be secret. Everybody can know about it. So this is what they are going to send. And based on this, they can come up with a shared secret. So how is it going to work? This is pretty simple, actually. So 0 is going to compute G raised to the X, and this is something he got already, because this is something he received. And he's going to raise that to the power of Y, his own secret. Ziggy is going to do the same thing, but using what he received and raise to its own secret. But what's pretty cool about that is that G to the Y to the X is exactly the same as G to the X to the Y. Eventually, you get exactly the same result. So this can be a shared secret. The shared secret wasn't sent explicitly. Both parties have a secret key that they never sent over the wire. They send something else that can be public. Anybody can take a look at G to the Y or G to the X. This is fine. X and Y are still secure. And based on this secret and public thing, they were somehow able to perform a computation together and come with the same result. So for that kind of thing to work, we need a function like this one. So it could be any number of parameters. But what's important here is that computing X is fast and easy. But given X, F, and just some of the parameters, finding the missing parameters is hard. So we know one of these functions already, maybe a hash function. We've been talking about that last time. So a secure hash function would satisfy the definition, but that wouldn't work for what we just did before. So if what we want is perform computations involving multiple parties, we may need something a little bit more flexible, where we can do more algebra. So if you read a paper about crypto or security proofs, you're going to see a lot of these acronyms, DL, CDH, DDH. What does that mean? This is just a set of problems that we assume to be hard. So the first one, given that somebody knows G, so this is completely public, and G to the X, find the X is hard. This is something that we want to be hard. And a lot of constructions in cryptography depends on this problem to be hard. The CDH problem is pretty much what we did just before. So we have an attacker, a passive attacker, who knows G and both public keys, but based on that, is not able to find the shared secret. And the next one is a refinement of the previous one. Given a shared secret or some random element, an attacker is not able to tell whether this is actually the shared secret or not. So as we can see, the DDH depends on the CDH, and the CDH depends on the DL. If the discrete logarithm problem is broken, everything is going to be broken. As of today, we don't have any proofs that the DL is a hard problem in the specific context that we want it to be hard. So maybe this is not the case, but a lot of people have been looking at it, and nobody knows of an efficient way to break it. So far, so good. The only efficient way that we know is to build a large quantum computer, but then we have another hard problem, which is how to build such a large computer, and we don't really know yet. Okay, so x to the y. Well, what does it even mean? Well, this is just an operation that we recursively apply y times. Okay, so it could be pretty much anything. So assuming that this operation is a multiplication, if we just do that without context in some kind of group like all the real numbers or even all the integers, well, we have a bunch of problems. First, the result can be ginormous, and we don't want that. In computer science, we want to keep things in control in a fixed number of bits. The second problem is that this is completely insecure, because if the result is large, it means that y is large, and we don't want to disclose any information about y. So this is insecure. We need a little bit more things, more context. One thing we can do is constrain all this computation within some range. For example, in Zig, we can use a nice type like U256 and an operator that wraps around. So the first problem is solved. Now we know exactly the size that it's going to take. This is nice. Well, the problem is still completely insecure. Why is it completely insecure? Well, for example, imagine that x is just 2. Well, in this case, no matter what y is, we only have 256 possible keys. So if we want something secret, this is not great. So ideally, what we want is to have nothing that divides the size of the group. So what we want is p to be a prime number. So unfortunately, Zig doesn't have any type like this one. 2 to the 255 minus 19 is a nice number, and it's in particular a prime number. So we don't have this type yet in Zig. So we are going to implement arithmetic mod 2 to the 55 minus 19. And this number has a couple interesting properties, especially for software implementations. This is something we are going to discover. So first problem first, how do we store such a number? Because it's a pretty big number. It doesn't fit in a 64-bit register. So what we can do, pretty simple, we are going to use more registers. We are going to store 255 bits in 4 64-bit registers, or even if it's not registers, 64-bit words somewhere in memory. So that works. We even have one spare bit that we can use for anything, maybe store the sign or whatever. So this is great. Simple. Given this, how do we add two big numbers? Well, that's pretty straightforward. A0 plus B0, A1 plus B1, A2 plus B2. We can even vectorize everything, and Well, not really. I forgot something, which is a carry. Every time there is an addition, it can overflow. So we have to add the previous carry and then output a new carry for the next step. So something that looked very easy to run in parallel now becomes a very sequential operation. You have to do this carry propagation in a very specific way. Okay, whatever. How do you do a multiplication? Well, same thing. I didn't write the details. Everybody knows how to do a textbook multiplication. Other techniques exist for fast multiplications, but they share the same problems. So we compute bit 0 times A0, bit 0 times A1. Everybody meets everybody. This is great. Well, there is more. For example, every time we do a multiplication, we can have a carry. So in addition to individual multiplications, we also have additions to make with carries to propagate. Okay, so eventually we get all the lines that I didn't write here, and then we have to sum up the columns. When we sum up the columns, we still have a carry to propagate every time. So we can do everything at the same time. However, there's a problem if we only have one carry bit in the CPU. Because a CPU can be very efficient using prediction and doing multiple things at the same time if there is no conflict or dependencies. Now, if multiple instructions are competing for the same thing at the same time, performance is not going to be great. So we would need to do two completely different addition chains at the same time, but with one carry bit, it's not great. Fortunately, on recent Intel CPUs, we have a bunch of additional instructions that can use two different bits for carries. So we can actually do two addition chains at the same time. This is not too bad. However, in order to use that, first we have to use assembly. There is no way to do that directly in Zig, and it's absolutely not portable. So maybe we want to do things a little bit differently. So you got the idea. Carries are annoying. So how to get rid of the carries? One thing we could do is instead of having 4 64-bit lambs to store our 255-bit number, we can add one more. So we have 5 64-bit registers now. So now we only need 51 bits per lamb. This is nice. We have plenty of extra bits that we don't use. We don't have to use 51 bits. We can use something different, such as a bunch of limbs with 56 bits, which is nice because it's a multiple of 8. So we can use permutations or unaligned moves. We don't have to do shifts to go from a packed representation to this one. So we can use pretty much anything we want. On a 32-bit systems, we can, of course, use less bits. But the idea is to leave holes, some bits that we don't use in each of these lambs. Why is that cool? Well, now if we want to do an addition, we don't have to care about the carry. We can do all the addition in parallel. There is no overflow. And what's even better, we can do a lot of additions before it's going to overflow. So that's great. No more carries to worry about. So this is pretty nice. And what about multiplications? Well, if we want to do a multiplication, the result is going to be twice as big. Well, it could be twice as big. So what we can do is still have 5 limbs, but instead of having 64-bit limbs, we're going to use 128-bit limbs. And this is going to be very efficient. LLVM can generate very, very efficient code for that. So this is great. We just do this. And we still have 51 bits per limb. Now, for the internal multiplications, we don't have to care about the carries. There is enough space for that. So we can do all the multiplications very quickly. For the additions, same thing. We still have a lot of space. We don't have to care about the carry. So we do all these multiplications and additions, and we can benefit from some parallelism at this point. And only after we are done, we can do a carry propagation. So this is faster. However, we may still end up with a pretty large number, which is larger than 2 to the 55 minus 19. I'm just going to say p instead of 2 to the 55 minus 19. It's smaller, shorter. So yeah, we still need to make sure that we are still within the bounds, because if we do another multiplications right after, it's going to explode. So what we can do is a reduction. In this case, we have 512 bits, and we want to perform this mod p operation. So a couple techniques exist to do that. One of them is a Montgomery multiplication. You have to transform your number in a specific form, and then you can do your multiplications, and you have to transform it again. It's okay, it works pretty well. It's a very, very generic solution. There are other solutions as well. We are going to see one of them later. But another solution is to have a very nice p to start with, a very nice number. And it turns out that 2 to the 55 minus 19 is a nice number for fast reduction. And this is why. How much would be, considering these bits, 1 followed by 255 bits, which are all zeros, which is just 2 to the 55. Well, this mod p is just 19. So what we can do for the reduction is take all the bits before 2 to the 55. If we multiply that with 19, then what we get is equivalent mod p to what we had. So we just do this multiplication, and then we add the result to the lower bits, and poof, done. So this is not a complete reduction, because we have this addition. We still may overflow a little bit. However, maybe we don't care. Maybe if we still have a bunch of operations to do, a bunch of multiplication and additions, this is still very small. We can carry on. And only after we are done, we can do a full reduction, which is going to be exactly the same thing, except that we are going to do this step just one more time. So as you can see, this specific number, this 2 to the 55 minus 19 number, hasn't been picked at random. It's been specifically chosen so that implementations can be fast. Okay, so x to the n, what does that mean exactly? Exponentiation. Well, it just means that we recursively apply something n times x. Okay, we said that already, but how do we compute an exponentiation, mod p? Well, we would do it the same way as we would it in any group. But if n is very large, we are not going to iterate n times. That would be super, super slow. So what we can do is decompose n into a sum. And then the exponentiation is just going to be a product of smaller exponentiations. So let's take a very simple example. If we want to raise x to the power of 10, there is a very simple way to decompose a number into a sum. And this is just a binary decomposition. We turn the number into binary, and we get a sum. So 10 in binary is 1010. So this is what we have on the right column. On the left, this is very simple to compute. We start with x, and we just keep squaring. So we are in a loop, and at each iteration of the loop, we square the previous result. And then we look at what we have on the right. Do we have 0? Well, we don't do anything. We don't multiply anything with numerator, which is set to 1 at the beginning, of course. And if we go to 1, then we multiply what we have with the accumulator. So eventually, we get the result much, much, much faster than having to do 10 iterations. However, as you can see, we do different things according to the different bits of the exponents. So if the exponents is some kind of secret, we can have some problems with side channels because processing a 1 is going to be slower than processing a 0. And we want to avoid side channels. So how to do that? Well, one way to do it is to use conditional moves. And rather than talking about it, I can just show you some code. We may have some right here. Let me just increase this. Okay. Do I have cmove here? Okay. So cmove is an instruction that you can find on Intel CPUs, and I think on ARM and most CPUs, you have pretty much the same kind of instructions. So what does it do? Well, it's a move, so it assigns a value to something. However, it only does it according to a third parameter. If this parameter is 0, the move doesn't happen. If the parameter is non-zero, the move happens. I was just wondering, can you see some code right now, or are you still looking at the presentation?
No, we're still looking at the presentation.
Oh, okay. That was not expected. So, okay, let me try to fix this. It will screen. Okay. What about now?
No, still presentation. Let me double check. But yeah.
You're still looking at the presentation?
Yeah. So let me think about
What?
this. It could be I think you gave permissions to Discord, right? To
I did, yeah,
yeah.
absolutely.
You know what you
Okay,
can try?
let's
You
try
can
to find.
disable screen sharing completely and restart it. So maybe that might
Okay,
fix it.
okay, no worries.
Mhm.
Entire screen, go live.
Okay, now I'm
So it
seeing
should be better
everything.
now, right?
Yes. Now we see
Okay,
cmove.
that's
Yes.
okay, perfect. So cmove is an instruction that you can find on most CPUs. That just does an assignment. It stores something into a register or to memory according to a third parameter. If the parameter is 0, nothing happens. If the parameter 1, the move happens. On most CPUs, it's believed to be constant time, which is nice. However, there is no way in Zig to directly produce this specific opcode. And if we use some assembly, then the compiler doesn't know how to optimize it really well, and it's not great. So we want some generic solution to do it. And one way to do it is this trick, which is very common. We just compute the difference between here, this is FE and A. We want to store A into FE if C is 1. So we compute the difference between FE and 1. Here, this is just a XOR. And then we apply a mask. The mask is either 0 or just all 1. So if it's 0, when we apply the difference, we wouldn't be applying anything. So no changes is going to happen. Now, if the mask is -1, just 1 bit everywhere, then we apply the difference. So the move is done. So in order for this to be constant time, we rely on the fact that the compiler doesn't know how to optimize this. As of today, this is the case, and I'm not aware of any compilers that actually optimizes this, which is great. It's still a little bit scary because it may happen. However, in Zig, we ship the compiler. We know exactly what compiler we use and what version. So we can get some confidence that this is okay to do so. And so many crypto implementations depend on this, that if this assertion ever breaks, we will probably know about it. Okay, can you see the slide again?
Yes.
Okay, perfect. So this is very cool. We can do additions, multiplications, exponentiations. What about divisions now? Why not? Okay, so a division, when we divide A by B, it's equivalent to just multiplication by the inverse of B. So if we can compute an inverse, we can divide. How do we compute an inverse? By the way, what's an inverse? Well, B times the inverse of B is 1. And this is something that's very easy to figure out with real numbers. But with integers in a finite field, when we can wrap around, we can totally find a number, an inverse for B, where this works. Here's a very simple example. Using a very small row size, we are going to say that P is 31. We have 7 times 9, mod 31 equals to 1. So 9 is the inverse of 7. So we can divide even with just integers because we are in a finite field, because we can wrap around. So great, we can divide, but how do we do that? How do we compute an inverse? Well, this is a little bit complicated, but there is a very simple method, which is called the Little Fermat theorem. The demonstration is not so simple, but the result is great. So this is only valuable if P is a prime, but if we raise B to P minus 1, mod P, we get 1. So an implication of this is that the inverse of B is just B raised to P minus 2. So we know how to do an exponentiation, so we can use that to compute an inverse. But wait, we can even do something better, because P is a constant. We know what P is. So maybe we can go even faster than what we did before with the binary decomposition of the number. Let's take a look at an example. We want to compute x raised to 200. Can we do better than what we did before with squarings and this binary decomposition? Well, yeah, here's an example. This is how you can compute x raised to the power of 200. So just a few steps, and you get this result very quickly. As you can see, each step is just reusing previous results. In this case, this is reusing exactly the line before, but it could be any previous result. This is called an addition chain. It can be used to compute multiplications or for exponentiation if you just change the operators. So this is cool, but how do you find such a chain? How do you find a very small chain that would be more efficient than what we did before? It's a little bit complicated, and I don't think we have an algorithm to find optimal solutions. However, we have a couple algorithms that we can combine to find solutions that are pretty close, or even the optimal solutions. And in order to do that, some tools can help you. The one I use a lot is, it's not Zig, it's called Async. I can maybe increase the font size if it's not too readable.
Yeah, it's pretty good.
Okay, perfect. So Async is written in Go, but it works. Maybe we need a version in Zig. Okay, so Async is very simple. You give it a number, and it's going to find such a chain so that you can multiply quickly with this number. So let's do it with a very concrete example. I'm going to use a different terminal, maybe. For computation, I like to use Ruby. It's a little bit weird, but I like it. So we had P equal to 2 to the 55 minus 19. This is the number we've been talking about. Pretty big number. And now let's take a look at the code. Here, if I look at the Jacobi symbol, okay. There is a technique that I'm not going to talk about to quickly check whether a number is a square or not. And in order to do so, you compute what's called the Jacobi symbol. And this is what we do. So to check that x is a square, you just raise it to p minus 1 divided by 2. Okay, so this is another case of an exponentiation that we already know about before, so we can optimize for it. So let's do it. So this is p minus 1 over 2. We want to raise to this super big number. How can we do that? Well, the traditional method probably works, but we can use an addition chain. So back to my tool, I'm going to type add chain, search this number, and wait a little bit. It's going to take a couple of seconds. Okay, so we can see a couple steps. So I don't know, maybe it takes 20 steps to achieve this super huge exponentiation. And if we take a look at the code, it's probably more readable than the description that we get from this tool. Jacobi symbol, where was it? Oh, it was right here. So this is what we do. 2 times 1, so 1 represents x, it's just the unit. So this representation right here, 2 times 1, just means that we take the unit and we square it. This is what we do in the code. Well, after we square it, we add, so we multiply, it's a plus here, but in the code, because we do exponentiation, this is a multiplication. So we multiply this square with a, and then we square it twice, and so on and so forth. So you just apply this recipe, and you get something which is sometimes way faster than using a binary decomposition. It really depends on the number. Sometimes chains can be very optimized, sometimes not so much. But yeah, for pretty much everything we have in Zig, I just use this tool, add chain, because it's nice, it works. Okay. So let's go back to the presentation. Well, where was it? Boom, 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 keynote, perfect. Perfect. We know how to do additions, multiplication, exponentiations, inversions. So we know how to divide if we want to do that. How to do square roots? Why not? Well, what is a square root? Same thing for real numbers is pretty easy to understand. But a square root is just something that when you square it, you get this something back or some equivalent. So if we are within a set of integers and we wrap around, so we have this finite field, we can probably find something that satisfies this equation. But how to find that? Well, this is complicated. There are some generate methods, and they are a little bit slow and complicated. The best one has been published just about 2 weeks ago by Sarkar. So I just put the link here. It's pretty interesting techniques. The most common one is the Tonelli-Shanks technique. These are great, but still we can do better, because for some specific primes, we can go faster. Just some. They have to satisfy something very specific so that we can apply another technique, which is just doing 1 or 2 exponentiations. So Atkin discovered that if we have p equal to 5 mod 8, then we can just do 1 exponentiation to have a square root. And it turns out that 2 to the 55 minus 19, what a surprise, satisfies this. So we can quickly perform a square root operation. This is super nice. Plus, as you can see here, this is a constant. So once again, we have to do an exponentiation using a constant so we can optimize for it. That gives us one of the roots. Once we have the positive root, we just square it to see if it works. If it doesn't, we have the negative root that can work. So to get the negative one, we just multiply by square root of -1. We check if it works. If it does, cool. If it doesn't, there's no solution. In either case, this is super fast, just because we have a nice prime to start with. Cool, so we can do a lot of things. Negations, I'm not going to talk about negations. This is pretty straightforward. So in mod P, we can do additions, multiplication, exponentiation, inversion, square roots, everything, even if we don't have real numbers, just because we have a finite field, and in particular, a prime field. So this is what we got, a nice prime field. Hey, remember the problems that we were trying to make hard? We just needed some context for this problem to be hard. Well, we can do exponentiations. So maybe in this context, when we do everything mod P, the problems are hard. This is why we've been doing all this, right? I got some bad news for you. Nope, it's still not secure. For that to be secure, we will need a much, much, much bigger field. Wow, why did we do that? Come on. Let me show you why. But first, let's try to do arithmetic without numbers. We've been talking about numbers too much. So, no more numbers. And we are going to take a look at vectors. So, not vectors as in Zig, but just geometric vectors. Okay, so we have one short enqueued vector. And if we take this vector and we add it to itself a couple times, we can create other vectors. So once we have other vectors, we can add them together. We can subtract vectors. We can do some kind of computations using vectors. So we know how to add vectors. What we can do is multiply two vectors together, because it doesn't make any sense to multiply geometric objects with each other. But we can multiply a vector with a scalar. We can multiply a vector with a number, which is just adding it to itself a couple times. We can do that. So we're not really looking at numbers here, just pure geometry. Okay, vectors are interesting. Let's make them a little bit more interesting. But yeah, before that, we saw x to the n, and I told you before that what we did is take some operation and recursively apply it n times. But this operation can be anything. It could be a multiplication. This is what we did before. But here, we don't have multiplication. So this notation will actually mean adding x to itself n times. It's the same thing. It's just a different notation. And we could have used a multiplicative notation for that. But in crypto, it's much more common to use this specific notation. But it just means that we just add x to itself n times, which works really well for vectors. Now, let's do something more interesting. We keep these vectors, but we are going to bend them a little bit to make them fit on a track, on a circle. So we have a nice circle with a start. It's nice to start from somewhere. So this is a point 0. And we still have our vectors. So now they just go on the track. So we can still do operations on that. We can still add vectors, subtract vectors. These are not really vectors anymore. What we are doing is actually more computing on angles. We are just adding and subtracting angles. But still, we can compute with that, with angles. We're not talking about numbers anymore. This is just geometric stuff. However, it doesn't seem like we are taking advantage of the geometric object itself. We are just using angles, but it could be just a number and we would get exactly the same thing. So it doesn't make the problem more complicated. So let's keep the nice circle. And we are going to define a way to do an addition slightly different. For example, we have 2 points, A and B, and we want to compute A plus B, which is going to be another point. So let's define a rule to do that. For example, one thing we can do is draw a line that goes across A and B. And then we are going to find a parallel line that crosses the starting point. And it's going to cross the circle at another point. And we are going to call this point the sum of a plus b. And this is a classic way to do an addition over conics. And that works really well. You can do a lot of additions and you're going to jump around, but always stay on the circle. So all the points will satisfy the same equation, the equation of a circle, but still, you can do any kind of arithmetic you want. And this is pretty cool. However, this is not secure, but the idea is not too bad. So let's make it a little bit more secure. Oh, just before that, a specific case is when you want to add a point to itself. Well, in this case, you just take the tangent and you do exactly the same thing. So if you want to compute 2a, this is just a plus a. Well, you do it that way and you get the sum. So you can multiply a point using this. However, this is not secure. But if we use something pretty similar using a more interesting curve, now things can become a little bit more secure. These are elliptic curves, so different kind of curves exist with different forms for their equation. This one is probably the most classic one, if only because it's very easy to visualize how the addition works. So this is what we do. We have point A, point B, and we are going to draw a line that goes across A and B. And this line is going to come across another point on the same curve. And that point could be A plus B. However, if we do that, we have a problem. Because what would be A plus B plus A? That would be B. We would be jumping back and forth forever. This is not cool. We need to improve that. So we are going to apply a very simple tweak to that. We are just going to flip the sign of y. And then it works. We're going to get a different point every time. We are always going to get a point which is on the curve. So all the points will satisfy the same equation. And we can do additions. So if we can do additions, we can do scalar multiplications. We can do a lot of interesting things. So what we had on the slide before was some pretty cute visualization. How many points do we have? Well, on this specific visualization, we were probably using real numbers. So we have quite a lot of points, like an infinity of points. We probably don't want that. We want things to stay manageable. So what can we do? Well, what we can do is say, all right, the coordinates, x and y, are going to be integers. It's a good start. And integers in a finite field. So maybe integers between 0 and p. And then the curve looks like the background, like points all over the place. It looks like a big mess. But all these points satisfy the same curve equation. And we can still do additions exactly the same way as we did before, even if we can't visualize them really well anymore. It still works. So how many points still satisfy the equation? Of course, it depends on the curve. It depends on the equation. In Zig, right now, we have two main curves. In the Zig crypto library, we have curve 25519 and another one called Edwards 25519. You can see the equations. They are pretty short and simple, but both curves have exactly the same number of points that satisfy this equation. And this is a pretty large number. It's pretty close to 2 to the 55. It's actually bigger than that, a little bit bigger. So this is pretty cool. What we're going to do now is pick a point. So just pick a random point on the curve. And if you're lucky, actually not too much, because it's pretty easy to find a good one. What you can do with this point is add it to itself many times. Of course, you are going to stay on the curve all the time. And because we have a finite number of points, after a while, you are going to come across a point that you already saw before. So you get a loop. So how large is the set of elements that you can visit before you go back to square one? Pretty large, about 2 to the 252. So that's still pretty large. It's not 2 to the 55, but it's still really, really large. And it turns out that this number is not only large, it's also a prime number. So you know what? The problem that we are trying to make hard since the beginning, we can compute them using this new kind of way to compute. We have a prime order graph, and we can do computation on that. So that's pretty cool. And what's nice is that when you have a point, if you need to multiply it by a scalar, you pretty much have to do all the steps in order to compute it. There's no very efficient shortcut to find directly the right coordinates. Well, you can still go faster than doing all the additions, of course, but there's no super fast and super efficient shortcut to do that. And because of that, all the problems that we were trying to make hard at the beginning are now hopefully hard. Hopefully, because we don't know, but we hope that these are hard. So the benefit for that is that we can do a lot of crypto things with very small keys. Because the problem is hard, we don't need very large keys. And this is great. Now, remember, we picked a random point, and by chance, we were able to generate a graph which had this size. Now, if we pick another point, what could happen is that we can keep adding this point to itself many, many times, and we can generate a graph which is even bigger, which is not a problem. That's cool. Or if we try again and pick another point, we can just add it just to itself, because then we wrap around already, or just twice, or just 4 times, or just 8, and then we are done. So for some points, we get very, very, very small graph. This is not great, because if you receive a public key, which is within one of these graphs, and you multiply it by a shared secret, by your own secret, to generate a shared secret, well, the shared secret is not going to be very secret if you only have 8 possible values for it. So that's super dangerous. We absolutely want to avoid doing stuff in these very small graphs. And we are going to see how to do that, but not now. Let's talk about implementations of all these things. First thing first, how can we represent a point? Well, there's a very simple way to do it, using affine coordinates, x and y. Okay, so exactly like we saw on the curve, pretty straightforward. Okay, now if we have coordinates, how can we add points? Now things are very complicated, so there's a simple way to do it, which is this website. This is the Bible. This is where you have all the explicit formulas to do additions and doubling over a lot of elliptic curves. So let's take a look at this website. Oops. Because it's really cool. So it's a pretty ugly website, but it's very useful no matter what. It looks like this. So we have different kinds of elliptic curves. You can see the form of each elliptic curve. So, for example, for Edwards curve, which is Edwards to 5519 that we have in Zig, this is what the equation looks like. Could be any D right here, any A, but this is a general form of twisted Edwards curve. And the website tells you, okay, this is how to add 2 points. Maybe I can just increase the font size. This is how to add 2 points. And this is how to double a point. So how to add a point to itself. So this is pretty cool. So we can just apply that. So let's take a closer look at this. And we can see that we have divisions. And a division implies doing an inversion, and an inversion requires some exponentiation. And it's okay, but this is not the fastest operation. If we could avoiding divisions, it would be nicer. So how can we do that just to go faster? There is a very, very simple way to do it. Instead of using divisions, we are going to represent coordinates as fractions. So instead of storing x and y, we are going to store x over z and independently update x or z. If we want to divide by something, z at the beginning is 1, and we are just going to multiply z by whatever we wanted to divide x with. Multiplication is super fast. So we just maintain the denominator and the numerator independently. And only after we are done with all the computations, we actually perform the inversion to recover the real value of x. So this is much faster. We only have one inversion to do instead of having to do one every single time. So if we look again at the explicit formula database, you can see some representation for fast computations for all the kind of curves. So it's telling you stuff about extended coordinates and projective coordinates. So projective coordinates is exactly what we've been talking about. Instead of storing directly x and y, we store them as fractions. And then the formulas have been adapted to use this specific representation to be faster. And it turns out that it could be also quite efficient to keep the product of x and y around. If you have this in your set of coordinates, computations can be faster. So we have different ways to represent a point. Affine coordinates, just x and y, projective coordinates, like fractions, extended coordinates, which is the same thing, except we have a t in addition to that, which is just a product of big X and big Y. So we can take a look at the code. Still looking at this. Okay, so now this is not in field.zig. We are going to take a look at Edwards 25519 because this is what we've been talking about. And what we can look at, let me increase the font size a little bit more. And the window size, okay. Oops. For example, how can we add, this is doubling, but okay, this is how to add 2 points, for example. So that's pretty simple. And this is one of the formulas that you can find on the website before. And this is just a bunch of computations over the coordinates. Everything is mod p, but we have already written everything for that. So this is an addition. This is doubling. And you can see that a coordinate is just this, x, y, z, t. And all of them are field elements. This is an element in the 0 to the p range. So all the points are represented that way. And we do some very simple operations like this. Okay, now back to the presentation. So scalar multiplication, which is what we've been talking about before with other kind of curves, which is just starting with a point. We are going to add it to itself a couple times. So if n is really large, this is going to take forever. However, we can speed up the computation using exactly what we did before for exponentiation. We can do, for example, a binary decomposition of n, and then keep doubling p every time. So here is an example. We have a point p, and we want to compute p times 26, which is we take p and we add it to itself 26 times. 26 in binary is 1, 1, 0, 1, 0. So in a loop, we are going to compute p, 2p, 4p, 8p. So we just double it at every step of the iteration. And then if we have a bit set to 1, we are going to add it this is not an accumulator, this is just a point that will be moving. It starts at the origin, and then it's going to move or not according to each bit. And that's it. So this is a way to do an efficient scalar multiplication. Still, if we have n, which is like 2 to the 56 bit, we need 2 to the 56 operations. That could be a little bit slow. So in this case, we would need 255 doublings and 255 additions to complete scalar multiplication. Can we go faster? Here's a trick to go faster. What we can do is pre-compute multiples of p up to, for example, 15p. So we do that. After we have this pre-computation, what we can do is, instead of taking the bits one by one, we are going to take them 4 by 4. So this is just the beginning or the end in big endian representation of n. We are going to take the last 4 bits. And what would be the value of my point multiplied by these 4 bits? Well, we can compute this bit by bit, or we can just use what we already pre-computed. We already know everything for 4 bits because we have pre-computed everything between 0 and 15. So we just do a simple lookup, and boom, we have something for these 4 bits. What are we doing next? Well, we multiply the point by 16, just using a couple doublings, 4 doublings, and then we switch to the next set of 4 bits. And we do the same thing. We already have a pre-computation table, so we reuse it. So this is faster. And you know what? What we've been just doing is exactly the same thing as just decoding hexadecimal numbers. This is what we do when we convert an hexadecimal representation of a number to the number itself. We take things 4 bits by 4 bits, and we multiply by 16 every time. Well, we are doing exactly the same thing, using points and geometry and a bunch of random stuff underneath, but this is exactly the same thing and the same optimization. So why are we doing that? Well, because now for n up to 2 to the 56 bit, we only have 248 doublings in the main loop, and only 64 adds, plus 14 adds for the pre-computation. And some of these adds could be doublings, and doublings are a little bit faster than adds. So this is more efficient, even though we have to do some pre-computation. Hey, by the way, remember the problem that we had with this specific set of curves? Other curves don't have this problem, but these have it. That was the fact that sometimes you may end up in a very small group, and we want to reject that generally. You don't want that. If you receive a public key and it's in a small group, it doesn't smell good. You just want to send an error and not go any further. So how can we detect if we are in a small group? There is a very simple way to do it. Given the size of these groups, we multiply the points by 8. Because I don't know, if the value you get is 2, 2 times 8 mod 8 is 0. Everything mod times 8 mod 8 is going to be 0. So we can do that. Once we have finished the computation, we do a couple more computations just to multiply the result by 8. Wait, we don't need to do that because we already have a pre-computation table. We already pre-computed 8q at the beginning. So we can just check that we are not in a small group when we are doing the pre-computation. If this is the case, this is not even worth doing any more computations. We know that it stinks. So let's take a look at the code for that in Zig. And actually, I'm just going to switch to the 0.7 branch because some changes have been made recently and it's a little bit less readable. Okay, Zig and 0.7.x. Okay. So let's take a look at the code doing all this. So the pre-computation is done in a very simple way, and it could be faster by using doublings. I'm just using additions because I'm really lazy. So this is just building a pre-computation table. Very simple stuff. Oh, I'm not sure that this is the 070 branch. That code looks more complicated. Let me try to just reload the file, pre-compute. Okay, this is easier. Yeah. Okay, so same thing. We start from the identity element because this is 0. This is the first slot of the pre-computation, and then we'll just add P to itself, pre-computation table. And then how do we do the multiplication? Well, we take bits 4 by 4, and I just call this bit, which is a little bit confusing because it's multiple bits. I think I changed the name recently in another pull request, but whatever. And then if the bit is not 0, we do the addition. If not, we don't do anything. And you can see that we have two versions of this addition. This one is constant time. PC select is going to use cmove to do the lookup in the pre-computation table. And this one is just a if. Sometimes we don't care about constant time or not. For example, if you do signature verification, everything is public. So it's okay to have side channels. We don't care. There is no secrets here. Sometimes we do care. So usually we need two versions of the function, but because this is Zig, we can just use CompTime and we get two versions of the functions. Okay, so this is what we do, and then we multiply by 16 right here. Cool. Okay, we're almost done. There's a trick to make things even better, because we had a pretty large, well, not so large, 16 elements pre-computation table, but we can still process bits 4 by 4 and have a smaller pre-computation table. This is the non-adjacent form trick. So how does that work? Well, let's take a look again at the scalar that we wanted to multiply a point with. So just the n. So we have a first group of 4 bits, b0, b1, b2, b3. And this in decimal is just 10. This is just an example. And then for the next 4 bits, we get 5. Okay, cool. So now we are going to take this 10. So we start from the end, 10. And because 10 is bigger than 8, we are going to remove 16. Okay, that sounds a little bit weird at first. So we get minus 6. Okay. So if we multiply the points by minus 6, we would be totally off. To get the correct result, we need to add 16. Okay, so let's go to the next set of 4 bits. And 16 for the next set, which is like the next digit, is just 1. So essentially what we have is a carry of 1. Okay, so for the next step, we add 5, and 5 is not greater than 8. So we don't change it. We don't subtract 16. But we have a carry. So we add this carry, and we find 6. And now, this form, having minus 6 here and 6 here, when you perform exactly the same computations, the multiplication by 16 at every step, you get exactly the same result as with this form that we had at the beginning. This is the same thing, just a different representation. But the cool thing is that in the second form, all the coefficients are in minus 8 and plus 8. So we can have a pre-computation table that only goes up to 8p. And doing an addition or a subtraction, this is the same thing. We don't even need different pre-computation tables for that. We just need to flip a sign. So we only need a very small pre-computation table, and we can still process the number 4 bits at a time. Okay, we are almost done. Just a couple cool applications for comp time that I found while implementing all these things. First, pre-computation tables don't have to look ugly. So let me show you what I mean by that. Remember that to generate a public key, we started with G, which was some value that both parties knew in advance. This is completely public. So we have the same thing for elliptic curves. We have a base point, which is well defined. Everybody's going to use the same. So we can already have a pre-computation table ready for this base point. This is going to make things a little bit faster if we reuse it. And traditionally in crypto libraries, you're going to find very long arrays with all the pre-computation tables hard-coded. This is super ugly. But because this is Zig, this is how the pre-computation table looks like. Where is it? This is how it looks like. We can generate everything at comp time. And you know what? This is the specific thing that made me love Zig. All this 25590 thing is what I started to work on when I discovered Zig. And the file that you're looking at is one of the first things I wrote. And when I found this, wow, you can generate the pre-computation table at compile time. You don't have to hard code everything using a different program, whatever. This is amazing. So that's cool. You can pre-compute stuff that way. Another nice use case for comp time that I found is in a completely different thing. So if we take a look at scalar, for example, I'm not going to talk about this. This is yet another prime field. But what's more interesting is the reduction. This is using a different technique for reduction because this is not a nice prime. So this is using a Barrett reduction, whatever. So this is still a reduction. So we have a pretty large number and we want to compute mod some prime. However, the number is not always large. Sometimes it can be 512 bits. This is the maximum we support here. But sometimes we know that it's smaller, maybe 256 bits only, or even less. The usual way to address this in an efficient way is to write different versions of the function, which are pretty much the same, actually. And what we can do using Zig is tell the compiler, this is a version for the largest size that I want to support, 512 bits, but we have some invariants. So if the lim count is on only 4, for example, I know that a bunch of parameters are going to be 0. And then the compiler is going to produce a specialized version with everything that can be optimized knowing these invariants generated automatically. I don't need a specific version of my function for different sizes. I just fix the invariants, and the compiler does multiple versions of these functions for me. And I found that really, really cool. Okay, I think we are almost done. So just another thing, I found that checked arithmetic is super useful in order to check for overflows, to check for bugs in your code, to check if you properly do carry propagations at the right time, for example. Doing that by default in debug mode is amazing. I love it. If you look at the standard library, there is std.mat.big with some really, really cool stuff to work with big numbers. This is really cool stuff, super useful stuff. However, the reason I didn't use that, well, a couple reasons. First, we want everything to be free of side channels, and this is not the purpose of std mass big. So we need to re-implement things for crypto. Another reason is that for these specific curves, we need specific field size. We know what they are in advance, so we can do some nice optimizations that we can do with a generic implementation. Okay, once we have that, we can build a bunch of super interesting stuff. But because we are running out of time and because I want to give more talks, I'm not going to talk about actual applications of what we just saw. Sorry, but thank you.
Thank you very much, Frank. That was awesome. So let me bring up the other view. I'll bring up myself. Okay. Wow, thank you for this talk. So it's been I had flashbacks from university when you started talking about like curves and everything else. I think though that my
Sorry for that.
teachers, yeah, my professors didn't do as much of a good job when it came to like visualizing stuff. That was very very interesting. So at least for me. So thank you very much. Um, So let me think about a couple of questions. So actually, first question is: so you mentioned like this pre-computed table and how you're able to pre-compute that at compile time and everything else. So how much, like, what are, because when you said the original one had, I believe, you said you had fixed 16 elements in it, but then you were able to reduce it to 8 in certain situations, right?
Yeah, well, actually, this is all about trade-offs.
Mm-hmm.
If you want to be as fast as possible, you can compute every possible combinations
Sure.
for every single limb. Then you get a ginormous table. It's going to be super fast. This is something you can do for the base point, for example. This is something I do in libsodium, which is one of the reasons it's fast. But in Zig, we don't want a standard library with a ginormous precomputation table because we want all this code to run well everywhere,
Mm-hmm.
including on small devices with not a lot of memory. So these are trade-offs. So one thing I do for that is keep the precomputation table just to 16 elements, even if it could be bigger, especially if we know in advance the points that we are going to start from. Then we have this trick to pre-compute only 8. Well, actually 9. So if we do that, this is faster because we don't have to pre-compute as much as before. However, we have more tests to do because for every single step, we can either add or subtract. Plus, we have to put everything into this non-adjacent form before. So that has a cost. And in real world benchmarks, I found that it was only interesting to do that, this non-adjacent form transformation, when you had a very large computation table, which is not what we have, or when you don't need constant timeness. So you can do this addition and subtractions just using a if statement instead of an equivalent, which is constant time, which is why it's only used for batch signature verifications. And then we get a small speedup. But for everything else, I still use just the 0 to 15p table.
Mm-hmm. I see.
Just based on real benchmarks. I was just talking to people on Discord. They run a bunch of benchmarks on different machines for me, which is super nice. And then I realized that it was worth it, but just on a specific case.
I see. I see. Well, thank you. Yeah, I remember you asking people around. By the way, there's a comment by Nectro, who I'm assuming Nectro is Megan on Discord, so you can find her. If I'm
I know
mapping the name
Megan.
correctly, you can find her on Discord. So the comment is, well, I guess first of all, it's incredible talk. So yeah, I agree. And she's pointing out that the pre-computation temple would only be included in the application if you compile it using the crypto algorithm. So it wouldn't be there every single time. Yeah, which I guess it's a fair point. But then if you do use this crypto algorithm, then you would have everything in the executable, and maybe that's too much for an embedded device. So the problem
Yeah,
would be there.
absolutely, especially for signatures, because even for IoT stuff, it can be pretty common to check and verify signatures. And we don't want a lot of code for IoT stuff. We want to keep things small, manageable. Maybe one thing I can do is if we compile with release small, I don't include the full table. If it's in release fast, then I can include everything. But I feel like this is a more specialized thing that should probably be in a different library rather than a standard library, and keep the standard library as lean as possible. Yeah, it's all about trade-offs.
That's a very good point, actually. What you just mentioned makes sense. Also, Komari Spaghetti was saying something of the sort in chat. Like you could still make that a comp time switch of some kind. But I agree that the general. There is one point which I think we haven't been discussing yet, and I think Andrew hasn't even precise the direction in that regard. And like, what should the standard library be? And like for me personally, I agree on the point that it should be not overcomplicated. While I understand that crypto is a bit of a particular subset of things in the standard library, like for me personally, I think one of the constraints that should be considered for the standard library is that the standard library should be not too hard to understand and should show like good use of Z primitives and like it should. I think the standard library should be considered a minor resource for people learning the language, not a major one. We should not expect people to learn language by reading the standard library, but it should be one of the things that they consult. And if you overcomplicate everything for specific use cases, then you kind of make it harder for people to do that.
Yeah, I totally agree. Yeah.
Okay, so you're getting a couple more compliments in chat, but I think there are no questions because you killed everybody with all the algebra.
I try to keep things pretty light, but yeah, there was a lot of things to cover.
Yeah. No, makes total sense. So, well, I'm looking forward actually to the next talk then, when you talk about all the other stuff that was in the final slide, Restret and everything else. So that's cool too.
Yeah.
I don't know. So what about Kumari's question, which is, oh, no, I think we covered it. Sorry, I'm reading chat and trying to make sure I don't forget anything. So I guess at this point, since I'm not in a position where I can ask you complicated questions about the discrete algebra and everything else, I'm just gonna ask you. So, how's it going? Are you enjoying yourself working in the Zig standard library? What's the best thing about it? What's the worst? Is there anything else that you want to report to the people watching?
Well, my experience so far has been really, really good. I mean, this is the main reason I keep using and enjoying using Zig so far, because crypto is something I know and like, and this is what I started to contribute. But I got some nice feedback right away, and my pull request got merged, and that was very encouraging. And I feel like, well, you can just look at how many people are contributing to Zig right now, but this is probably something that everybody's feeling. The fact that every ID seems to be welcome. And even if it's not, there are some constructive discussions every time. So this is great. This is not something where just one person controls everything. There are discussions about everything, and everybody can bring what they can to the table. And this is why the language gets better and better every day. So that's super cool. And contributing to the standard library is pretty simple because, as you said before, everything is quite simple to understand. It's not well organized yet. Things are getting better and better, but it's something that can be super useful to understand Zig first, because you have a lot of great idiomatic code in here. And then it's something that's worth contributing to, because when you contribute something here, it's going to be useful to many people. So yeah, that's cool, and everybody should do it.
So related to what you were just saying about the standard library, what is your position with regards to having a super lean standard library that only contains basically what the compiler needs plus a minimal set of features versus going for the full battery included approach? Like for you, what is a sweet spot that you think would make sense for Zig?
So having a minimal library is not that great in my opinion, because if you take a look at what happens with Rust, and Rust has a pretty nice standard library though, but even for very simple stuff, you need dependencies. You need a ton of dependencies for everything. And dependencies break, API changes. So even for very simple stuff, you spend a tremendous amount of time just trying to keep up with dependency changes. This is a waste of time. Whereas when you take a look at Go projects, of course, Go projects have some dependencies, but for a lot of very common stuff, even for HTTP, whatever, you can just use the Go standard library. So everybody is using exactly the same set of functions. So when you try to read a different project, you know how it works because everything looks familiar. Then APIs don't break, or when they break for everybody the same way. If everything is well documented, if you need documentation, everything is at the same place. Everything is maintained the same way. So having a rich standard library, in my opinion, is great because having dependencies is nice when you need something that's not very common, some very specific application. Okay, it doesn't make any sense to implement a blockchain directly in the standard library, for example. But everything that people need constantly, that should be in the standard library because having dependency is always a problem. Yeah.
Okay. Well, thank you for sharing your point of view. I think it makes sense. Like, I honestly have yet to find my personal opinion on what it should be. But one thing that I'm thinking is that going super lean, like going to the extreme of saying we just go include in the standard library what the compiler and maybe package manager needs, as if you think about it in like there's one way of looking at it is that you're basically creating a standard library optimized for writing compilers, and that's not what people should do with the
Yeah, right.
language. So
Well, some people may be happy with that.
oh yeah, sure. So there's another I think interesting point of view. Okay, thank you very much for the talk, also for answering questions. I'm looking forward to organizing a session then where hopefully we can find a few people. As I mentioned also in the beginning of the show, you are working with Jacob and Joachim also. Well, I don't know if Joachim is tackling the code signing stuff, but Joachim is working at the very least on the AMD64 code gen. So there's a lot of effort being spent on supporting Mac, and Apple decided to throw a big wrench in everybody's plans. So on one hand, while on the other hand, it seems that the M1 architecture is amazing in many other ways. So there's
Okay,
always
yeah,
this
it's fast. Yeah.
it's always this weird combination of things. So I'm looking forward to organize some kind of like fireside chat. Maybe that's a good way of describing it, where we can bring up a few people and discuss what's up. Thank you again, Frank. Is there anything else you want to say before we move forward?
Have fun.
Okay, thank you very much.
Thank you.
Okay, so I guess we are now moving to the 10-minute break in the middle. You're allowed to tap out if you want. But come back because we're going to talk about async await. And it's going to be a curious async await talk. It's not going to be super heavy, don't worry. I won't go into details. And you can think of this as a precursor to a full-fledged async await talk. But if you've tried to investigate a little bit what's up with async await and found it confusing, and especially if you were used to being able to use async await in other programming languages, this talk might help you find your way a little bit. So stick around and see you soon. Okay, thumbs up. Give me just a second to set up everything. So that's a view, there, green pointer from beginning. Let's hope I didn't mess up any of the animations. There's no way I did, right? um, okay. Is this correct? Yes, it is. Hey, hello, and welcome to why async await in Zig is not that easy. I guess I should say it's not that hard either, but it's undeniable that well, I can talk for myself. I didn't fully understand how everything worked. And I mean, one could say that I still don't really understand everything, but I got to a point where I think I'm comfortable reasoning about most async await applications, and I can reason about simple event loop implementations. I'm no proti, but I like as a topic, async await doesn't worry me in Zig. Now, the problem is there are recurring discussions about async await, and you find them in Discord. You find them probably on IRC. I don't check that as often as I should, but you see recurring discussions about async await. So while it's not that hard, it's not easy either. Like, we should acknowledge that there is something interesting happening. So with this talk, what I'm trying to answer is the question of why is it hard? Why is it that even if some people have no trouble using async await in JavaScript, for example, they still don't find it super easy to have a full grasp of what async await does in Zig? So I'm not going to, so just so you know, the goal of this presentation is not to give you an understanding of what async await is, not yet. This is a preliminary talk that is just going to try to identify where the hard parts are according to my understanding. So again, it might be wrong, but if I am right instead, this should help you identify why things are hard, and it should help you then, navigate the whole issue a bit better, and you will know what to search for, and it will be easier then to cross that chasm, like make the leap and get to a point where you feel comfortable thinking about async await. This is one of the two goals. The other goals, in a sense, it's kind of the same, but from the other perspective, from the perspective of somebody that does understand async await, this talk hopefully should help you understand what is the missing knowledge in the people that don't. And so if you are writing learning materials about this, maybe this is something that you should pay attention to so that you can address common questions about async await. So let's get started and see where we can get. So just to reiterate, to be perfectly clear with the point, you're not going to get to the other end of this talk understanding async await. But if you have no trouble learning by yourself and you just need a little boost when it comes to knowing how to navigate existing materials and knowing what's up, maybe this talk will help you push further with your own independent learning. That said, it's not always going to be the same situation. There's going to be new materials coming up. I will personally work on more learning materials when it comes to async await in the near future. So this is not the final state of things. It's just to answer a need now, today, with the resources and the materials that we have. Okay, structure of the talk, 3 points. I'll quickly mention the existing materials. I'll try to point out some of the reasons why people find it hard to understand async await, and then I'll quickly say, well, what what are some things that you can try doing next after this presentation? So to start with existing materials, there are a couple of talks by Andrew about async await, but these are mostly Andrew giving status updates. So for example, in this one that I'm showing here, he's showcasing async await at a point in time where there was no event loop, I think, still, or it was being worked on. And so in his demo, he's showing, and also he's not explaining the concept of async await. He's, I guess, kind of assuming that you know what has to happen, more or less. And he's showing how async await, he's showing the feature where you can do a async call on a non-async function, and the resulting code will still be efficient as if you did a normal call. It's showing the how should I call it? It's showing the feature in Zig where you can just use async and await every time, and if you compile in single-threaded blocking mode, then all the code will still make sense, and you will not have a big performance impact because maybe you are calling into some async await abstraction that ends up doing nothing because all the functions end up being blocking. So everything gets he's showing that everything gets compiled away correctly by showing the assembly code, the generated assembly code. And so, for example, he's showing also a couple of examples of suspend and resume working, but he's like hacking a second thread that is acting as a like makeshift event loop. So again, perfectly clear if you understand what needs to happen for a async await system, like for a evented system to work. But if you don't, this is not the talk that is going to this is not the streaming session that is going to answer your questions. There's another one after that by Andrew where he shows a bit more of the event loop. Now the event loop implementation is completed, or at least complete enough to showcase stuff. So, but again, the concept is not that different from the previous talk. There's a blog post by Dweej, I don't know. But this is an interesting blog post, Zigtastic async. But again, this is another blog post by somebody that knows what's up and is just digging into the details. So this person is using Godbolt and like looking at the generate assembly code to see what happens behind the scene every time you use await or suspend or resume. What are these operators doing? In the detail, like he wants to know which like fields are being read and modified and used as in the computation, hidden fields in the frame data structure, fields that you cannot access explicitly when programming in Zig. So it's interesting, but it doesn't answer the question either. The most complete explanations of async await, I would say, are this one and the next one I'm going to show. And both happen to involve me, I guess. But in this one, I am not the one doing the explanation. It's Andrew. So this is a talk that Andrew prepared for RedisConf while I was still working for Redis Labs. And it's a talk divided in two parts. The first half is him explaining how async await works. And he's also here explaining how Zig allows you to express concurrency even if you can't, even if you are in a situation where you can't exploit it to obtain more parallelism, and it's still the duality, which is actually the one freaking awesome feature that Zig has when it comes to async await. The problem is, again, this doesn't answer the most basic question of, well, but how does the whole thing would work normally? This is not addressed directly too much in the talk, or I would say, well, it is, but it's not a hand-holding tutorial, let's say. The second half of the talk, it's just me demoing a library that I wrote in Zig that uses async await, but we're going to talk about that later in the talk, so I'm not going to focus much about it on it. But I mean, it's Redis Labs, Redis Conf, it's a Redis client. Spoilers. The next resource is my blog post on Zig's colorblind async await, and here I am guilty of the same crime. In which I'm not explaining how async await works, how it's implemented. What I'm explaining is just the syntactic trick and how and I try to give a feeling for how the syntax still is consistent both in blocking mode and in non-blocking mode. I, for example, made a point in this talk to talk about async await without even mentioning suspend and resume. It's been a while since I wrote this post, so I hope I'm not wrong, but I'm pretty confident that, well, even if I mention the suspend and resume, they're not being explained. They're not prominent in this explanation, and I would bet that I didn't even mention them because my point was, again, just to explain the new feature, the new stuff that Zig brings to the table. But again, this is not enough if you need a full introduction. Now, this is not a lot of material. I asked in Discord if people knew other blog posts on the subject, and we got basically no answer when it comes to this material. There are a few projects that do stuff with async await, but I'll briefly mention what the problem is. Like, the long story short is that there aren't really many examples that really show you what you need to know there, unfortunately. I should have made more slides about those. I didn't. Now I regret it. But these can help, but are not the point either. So yeah, and so there's not a lot of material, and what is there doesn't go from A to Z. It just covers a limited range of what you would need to know. So why is it hard? What are we missing? And I think the answer is complicated. So I'll introduce, I think there are two main branches to why this is hard to understand. And the first one, which is the minor one in my opinion, I'll introduce it by just mentioning a couple of common doubts that people have. And so again, these are not full answers, but if you happen to have if you had this question in your brain, maybe it can nudge you in the right direction. So again, not complete yet. So common doubts that people have, like one is like, what is the relationship between suspend and resume and async await? There seems to be asymmetry there, and you can say that suspend is the inverse operation to resume, and async is the inverse operation to await, and vice versa. But people tend to think that there is also a parallel between async and suspend and await and resume. And that's not really true. Like, you're trying to find a symmetry there that is not there. Mechanically, these things are all pretty different. And like await, like, and there is also some partial overlap between some of what of these things do. So unfortunately, you can't build an understanding based on capturing a abstract symmetry and parallelism between these four operators. Well, these two groups of operators, these two couples of operators. So you need to dig deeper. Another question that people ask is, well, what exactly is responsible for resuming suspended frames normally? Like, I know that I've been programming in Python, JavaScript, or similar languages, and I know, like, I'll use JavaScript as the example. I know that in JavaScript there is one single thread that is running my code, or like Node is not single threaded completely, but the main control loop is single threaded. You program it, you don't have to worry about concurrent access to like a global variable, because it's only one thread running your main code. So I know that when I'm writing async await stuff, there is a event loop that is juggling multiple threads of execution. And I know that it only does one thing at a time, but it keeps jumping back and forth. from one task to the other. Now, how does it know how to jump? How does it know which is the next thing that it should jump to? Because, like, if I'm waiting to read from a socket, how does it know when it's time to read the socket? Does it like try periodically to read? Does it have a notification system? How do timeouts work? So these are reasonable questions, and the starting point to understand this, as I said, this is one half of the problem, although it's not really half. I think it's like it's very minor compared to the second problem, which I'm going to introduce later. And I think that the starting point is to learn about kernel APIs, and by that I mean you should take a look at K-Event for macOS. Linux has EPOL. Windows has, I don't know. Sorry, Windows is always. I don't mean to say that Windows is necessarily bad in that regard. I haven't programmed Windows APIs on Windows. I think people that use Windows sometimes say they're nice. Sometimes they seem like a nightmare because things seem confused and undocumented. At least that's my impression from reading like people chat about this stuff in the Showtime Discord server. There's a channel dedicated to Windows Evented.io where you can find Leithdew and King and a bunch of other people discuss this stuff. So I don't know. My impression varies. Oh, and also Andrew in chat mentioning IO-ring. Yes, IO-ring is another one. So learning about these APIs tells you how the OS is notifying your application about the events. Now, the problem is, once you know about this, and again, in isolation, this concept is not really complicated. Problem is, once you learn about this, you are still missing how your application is orchestrating the other half of the problem. Because if you think about these APIs as them invoking a callback in your application, which is, again, I would say, might be not precise enough, might be a model not detailed enough, but it's a starting point. Well, I guess this is how I would think about it if I knew nothing and somebody told me, well, the kernel API calls into your application to tell you a socket is ready to read. Then the next question is, okay, then how am I going to structure everything around a callback? It's hard. How do I keep stuff locked until a callback is ready? Is this a promise system or what? I mean, and this is what you might think if you're coming from a higher level language, because you know that whenever you are orchestrating manually, resuming stuff, you tend to have promises, but that's not really it. So start by taking a look at how these kernel APIs work and what they provide. And this is the building block outside of the application that powers that brings, I would say, efficiency to the event loop, because this way the event loop doesn't have to constantly check that the socket is readable, for example, or try to resume tasks that are waiting on resources that aren't available yet. And also, I would final point on this, I would say that don't be surprised that there is a gigantic amount of variability in how these things work and how the application is structured on the other end. The way Python implements async await, the way JavaScript implements async await, there are, and I say JavaScript, but I should probably say even Node versus other JavaScript engines, probably, because they don't have to implement the stuff the same way. They just need to provide you with the same semantics from the side of the user of these APIs. The variability is astounding. I was surprised and kind of disappointed to learn how variability is there and how some things are bonkers. Anyway, so be prepared also for that. That said, as I said, this is not the full story. Like learning about kernel APIs, I think, gives you 25% of the understanding maybe that's required. I think the biggest problem is the second half, which I'm gonna try to express through a parallel. And I think that we, as the average software engineer that has lived their own life programming in higher programming languages, we are missing a mental model. And actually, I would say I'm saying we as higher level programming language programmers, because, well, that's who I am. But I would venture to say that this same missing mental model is also missing from people that have experience with low-level programs, because async await is a pretty high-level construct. And so if you look at the assembly code, it's not immediately clear how everything actually, how the whole machine, how the whole dance ends up, like everything ends up fitting together and the whole machinery works. There's a few, how can I say? I don't know, maybe if you are super comfortable with assembly code, you can deconstruct everything and it fits in your brain and everything is fine. But if you don't be surprised, because it's a pretty high level feature. That's, I guess, what I want to say about people that have experience, that can read assembly code and feel comfortable understanding it. Now, I said that I wanted to explain this missing mental model through a parallelism. So let me tell you about when a few years ago, I was trying to help a friend do his computer science homework. He was a freshman, like a first year in university, started computer science. He didn't know, he knew how to use computers. He would, like, he's one of those people that know how to, he knows the hardware market better than I do. And he knows how to build a computer, but he has no programming experience. He had no programming experience. So he wasn't somebody completely, tech illiterate, but he wasn't somebody that had like previous experience with programming gained, I don't know, by doing it as a hobby before joining university. So when you approach programming for the first time, and maybe the question is, think about when this was you, if you can. Because probably for the people here, this was a long time ago, but that's when you have to try to visualize. So let's say you have this simple program, right? We start with main, so we assume that the entry point is main, but then there is also another function foo defined in here, and we do these simple 4 lines inside main. So if you're new to programming, one way of visualizing this is to say that, well, we have an arrow that says which line we are executing, and we start from here. Well, we start from the beginning of main, and then we go down line by line, one at a time. So, well, the first line just declares the existence of x. Well, it also sets to 0, but maybe that's a detail that you don't care about much when you're learning. And then you notice that x is being modified. So you can even think of saying, well, x lives in that line, and I'm going to change what the value stored in that line is. Then we move to the next line, and my 3 disappeared because I did mess up my animations. Apologies. So there should still be a 3 there. So we move to the next line, and you've been, so function calls, maybe you don't know about them in the beginning, but they are not that hard of a concept, right? It's a procedure that gets bundled under a name, and it's reusable. So you know that we are calling into foo, and we are passing x. And then, again, this is another non-trivial thing that you learn after. This is not like a mathematics, like this is not an equation where both sides have to be true. Like this is not like x and x here. They need to be like, you'd have to find a stable point or whatever. No, you pass the current value of x downstream. Once you're done evaluating foo, then you set the resulting value into x. So this is not a gigantic. Some people have questions about this too, right? Maybe you did when you were learning, but you get through that. It's not that hard. So then you know that if you're calling into a function, there is like a subtask, a sub pointer that executes what's inside that function, and you pass in the argument, which is going to be 3. You substitute every instance of that argument here. Then you know, oh, it's 3 times 2, so the result is going to be 6. And then you know that the new value for x is going to be 6. And this should have been a 3 that changed into a 6, but it is what it is. Then, next line is print foo. Print foo x. Now, you're calling into the function again, and what you learn after a while is that you need to reset the state of the function that you're calling it, because if you call a function a second time, everything starts from scratch again. So n is not 3 anymore. N is going to be the new value of x when we call foo. So this is not hard to imagine because you can still use the same trick where you say, well, I'm gonna use where the number is written in the actual listing of the code to make space for my new value. I substitute the name with the current value, and I compute the new value, which is 12, and you print 12. Nice, this works, and you can understand programs this way when you're getting started. But at one point, you encounter something that kind of breaks this mental model, or rather, it forces you to think about something that you could ignore before. More precisely, if now main is still the same, but now foo is doing something different. Foo is a recursive function. It's computing something different, and the problem is that it's computing something different using itself. And that's a nightmare, because previously you could think of the lexical where where the name is defined, where a symbol is used, you can substitute it with a new value. But when foo, and when using a function 2 times to separate times, you just have to think about resetting foo with to a empty state. But when you have foo call into itself, you cannot use this spot anymore to put a value in, because you have to think about, and actually I think this should be, sorry, there's another error. I think this should be n plus switch this. So yeah, this should be n plus, sorry. So you have to think about the fact that foo survives, well, a particular call to foo survives before while the other call is existing. So you can't use this mental model anymore. It's not detailed enough. Previously, you could get away with it because the stack was still there, and yeah, that's the point. So the thing that you're forced to think about now and to understand and model the existence of is the stack. And it doesn't have to be the stack like in the practical terms of how it's implemented in our architectures, but you have to understand that there is some other space, a table somewhere else, where you need to keep track of n for multiple nested calls. And before it was the same too, but you were never forced to think about it because your simplified mental model was detailed enough to get you away with that understanding. Now, can you still remember when you used to be confused by recursion? For me, it's been a long time. But it's not a secret that recursion can be confusing. And I think that my hunch is that with async await, we are in a similar situation. Even though we are experienced programmers by most definitions, I think we still have a blind spot that probably our education nor our professional life has covered. Some people actually do. So, by the way, the point is, this is not for everybody, right? If you're somebody that had previous experience implementing event loops, yeah, I'm sure this is not going to apply to you. But if you've, I don't know, I'm a bioinformatician, so I've done bioinformatics and web stuff and enterprise development after that. And then I started using PowerPoint as my main IDE when I became a developer advocate. So, I never, this corner of knowledge of how a specific system works was never stressed. This was just a weak muscle in a sense. So recursion forces you to acknowledge that there is a stack. And async await forces you to acknowledge the existence of non-sequential multi-threaded control flow models. When you use async await is like a go-to on super steroids. So you now, before, you were used to a control flow that it was fairly sequential, you know what's going on, but now the control flow is jumping around in weird ways, and different threads are executing this stuff, not just one. So this is your new reality, and async await forces you, or more, I would say maybe more precisely, it's continuations. Continuations have been confusing, I think, since forever, and I think they have confused everybody in all of history. So it's non-trivial stuff, and it's non-trivial because it's forcing you to face something that you could easily factor out from your mental model earlier. Now you're forced to gain this new extra level of detail in your model to be able to understand what's happening. So let's mention a couple more common doubts. So I heard also questions like, well, what does suspending a frame mean in practice? And how can a suspended frame be running code? If you ask this question yourself, the answer, again, not an answer that is going to explicitly satisfy your understanding. It's just to nudge you in the right direction. The answer is that you're thinking of a frame as an active piece, but frames are actually just a bunch of data structures. It's a bunch of code plus some state. The active agents doing stuff are threads. So this question should be probably reframed in what is happening with threads and the suspended state of a frame. And the answer is not simple. The answer is not immediately trivial. So you need to get there. But you should not be thinking of frames as active things. They are passive things, at least in Zig. Another question that I heard is, well, if async functions don't have a stack, how do nested async calls interoperate correctly? And that's another interesting question, because like if you know that you have a bunch of async functions that call into each other and they suspend at different points, and then you know that a frame can be executed, that can be resumed by another thread. Are threads swapping stacks around or what? And I think some other languages do this stuff, but in Zig it doesn't happen. So how can that happen? And the answer is based on understanding the async calling convention and how some things become frames themselves, while some other things can get away without having to do that. And once you understand this particular sub-dance, like this particular set of dance moves, then you understand the bigger dance routine. Again, I'll repeat this every single point. It's fine if the answer that I gave right now doesn't really satisfy you. It's not meant to satisfy you. It's meant to push in the right direction people that are asking these questions that are on the verge of understanding. So these are another couple of questions that I heard somewhere else. So and the problem is then, so why does it hurt so much thinking about this stuff? What's up? And the answer is it's because you've been an async await user all your life. You never stress this muscle. And now with Zig, you are being forced to look at the metrics. Or actually, what I should say is probably not that you are being forced precisely, but now looking at the metrics is an option. In other languages earlier, like in JavaScript, I think it was never an option to some degree. Like you cannot inspect too much, or I don't know, maybe there is some metaprogramming stuff that allows you to peek into what's going on in the event loop. But the point is, it's not something that you would normally do, or that you would have to do to understand what's going on, because your level of understanding at that level of abstraction can still use the same simplified model. That said, it's not like Zig is forcing you to really... Well, I would say that if you're programming in Zig, you kind of want to understand a little bit more because you want to be more precise with how your program is structured than you would normally be with your average JavaScript application. But Zig is not really forcing you to understand everything. And as a practical, like case in point demonstration of that, I did this with OK Redis. I wrote OK Redis before getting to where I am now. When I started writing OK Redis, it was way before I would say I knew anything about epoll or k-event or IO ring. Not that now I know that much actually, but now I know a little bit more. At the time, I didn't know anything. Like if you ask me what is the kernel API on macOS that gives you notifications for events, I would say I have no idea. But I was still able to write this library, which is a working Redis client that works both in blocking mode and it works also in async mode, in non-blocking mode, in evented IO mode. So how is this possible? The answer is that going back to what I was trying to say before, while Zig is giving you more control, and you want a bit more control than JavaScript because ideally you should be writing more precise, more optimal software in Zig. You don't have to buy into the entire complexity if you constrain yourself to certain use cases today. Okay, Redis, as I said, it's a client library. It just uses this stuff that the standard library network, the networking part of the standard library offers. I don't use suspend or nor resume anywhere in this code base. It's just normal async await. It's not that different from what you would write in Python. Not exactly the same, maybe. As I said, maybe a little bit more understanding, but not the complete understanding of how everything works. So my argument is that if you want to start getting into async await, writing client libraries for stuff, it's a great starting point, because with client libraries, you can still be a async await user. You don't necessarily have to understand all the implications into how the event loop works and how the finer details of async await and frames are. So client applications are perfectly doable, maybe with a star, because you might find the occasional bug, I don't know, or because, for example, not all the async operators are there yet. I think there is an accepted proposal for another operator called select that allows you to kind of wait multiple frames at the same time and react whenever one is ready. Today, this is not really possible the same way. And so I wouldn't say that all client applications are perfectly doable, but especially when it comes to libraries I would say are nicely doable. And I would say maybe you can consider, okay, Redis is an example of that. I think one of the downsides is that I'm going a bit heavy with metaprogramming in it, so you might not find everything as straightforward as it should be if you were looking for something that shows you a usage example of async await. But that said, there is no weird async await stuff in there, and at the same time, it's something that actually works. So yeah, consider taking a look at client libraries. Also, another reason why client libraries are your best bet, in my opinion, today to get started is because applications, and more importantly, servers, tend to require resource management. Like resources tend to have life cycles, and that makes it harder. It forces you to think more about what the event loop is doing precisely, and you have a more active role. So server applications, server libraries, since they have to manage resources more explicitly, and complex client applications also have to manage resources, they might be a bit hard to get started. But client libraries are not, because they tend to, in the client library, you don't have to do much resource management most of the time. Or at least this wasn't the case for me with the Redis client. And I would bet that if you write a client for another database, as an example, you would probably find it that it's not that different, and that you also don't have to do much resource management, so you don't have to reason about the complex stuff. You can just use async await to make sure the stuff, ends up being easy to juggle in the whole overarching architecture of the final application. That said, you can still write simple applications that try your code. So you can write a simple, I have a bunch of example applications, test code, I guess. I think of it as test code that tries the client library and tries to do simple stuff. So it's not like you have to write a library, you can't use it. You can use it. The problem is when it comes to complex client applications that do a lot of stuff, because then you fall into this resource management conundrum that might be hard if you're just getting started. I have also a life hack. Do you really want to get to the other hand knowing a lot about how async await works in Zig? In my opinion, a great life hack is to implement an event loop. What I did was take the standard, the event loop implementation in the standard library, and in a fork of Zig, I removed every function in there. I wrote a simple script, like a simple script that just contains like a open a socket, write to it, read, close. And if you know in Zig, if you're not using a function, then that doesn't even get analyzed. So by having a super simple test application, you don't have to implement the entire API of the event loop. You can get away with implementing just what's actually needed for that use case. So that's beautiful, because then you know precisely which are the functions that interact in that specific subcase. You can take a peek at how everything is orchestrated into std.net and the upper level FS and FS and net and the lower level of OS. And you can see how control passes from one part to another. And then when I say re-implement what the event loop does, it could be even as simple as copy-paste back the actual lines of code that are needed to implement that, maybe trying to read them. So you need to find like a balance between, you need to do some work, right? But it's not prohibitively hard. I went from knowing nothing to understanding this, and I think you can do that too if you are just willing to put in a little bit of effort. So this is actually the conclusion of my talk. It's not more complex than this, and but there are a couple of takeaways that I think are important. So to really recap the points that I wanted to make. If you're interested in async await, consider writing a client library, and you can test it writing a small application for it. That will show you that you can be as productive in Zig as you are in your higher level languages when it comes to just being a sync await user. So you will see that since there is not a gigantic ecosystem of ready applications, you can't do everything with the same ease that you are able to in JavaScript. Like if you want a HTTP server, there aren't 10,000 HTTP servers ready for you. There's Apple Pie that is being worked on now by I think it's Firefox. Am I misremembering? Yes, no, it's Nipsey. Nipsey is working on Apple Pie, and I think there might be a couple more implementations. But again, maybe you try the application and it's buggy, and there's something that doesn't work as it should. So yes, today there are a couple of things that you cannot really do in Zig unless you implement them yourself, and implementing them yourself requires you to know more. But when it comes to standard client libraries, you can be really as productive as you are in other languages, and you can enjoy really how things are so much nicer in Zig. Like I loved that my Redis client has one code base for blocking mode and async mode. This is something that you can forget when it comes to Python or other languages. So it's not just doable; it's doable and nice. But if you adventure yourself into unexplored territory yet when it comes to server applications, unfortunately, yes, it's still you have to learn more once you start factoring in resource management. Another thing is, learn about key event, epoll, etc. But know that that's not the full story. And if you go that route, you might want to really take a peek at the event loop in the standard library and use that as a guide to really understand from start to finish how your simple open socket, write hello, read a line, close application works. Because you can do that by shrinking the scope of the main final application. You can shrink the scope of everything else that you have to look at in the code. And once everything fits into your mental model, then you start understanding more how everything works. That's still not gonna give you the full understanding when you start having multiple threads jumping left and right and moving control flow, but that's something that we can tackle in a different way. And and that's the final point. So my final point is understand that you might need a more detailed mental model for multi-threaded continuations. Like when you need to fully understand async await, you need to appreciate how it's possible for chunks of execution to move around without messing around with the actual stacks of each, interoperating correctly with the stack of each thread and how everything works. It's not crazy. Again, I'm not attempting to give a half-baked explanation of this because I would like to give a proper one in a dedicated talk. But you need to get there to really understand everything, in my opinion. And finally, I promise to work on some more learning materials soon. Just give me time. I'm working on the website, and maybe there will be other priority. But to me, writing stuff that help people understand async await, it's fairly up there as a priority, because I think it's a very exciting feature of Zig. So right now, I'm mostly, for example, waiting for select to happen so that I don't end up, preparing a talk on async await that doesn't mention select, which ends up being something very important, and then the talk becomes obsolete, like at the speed of light. So I'm trying to be, how can I say, efficient also with my effort, and there has to be a balance there. And that's pretty much it. So that's the end of my talk. Thank you for listening. I hope somebody here now feels a little less confused about this stuff. I know I didn't answer anything completely. I just gave hints and stuff, but at the very least, know that if you have trouble with some things, you're not the only one. It's not you having issues. We can get there. We just need enough learning materials, and the ecosystem to stabilize a little bit so that the learning material doesn't become obsolete in at the speed of light. So Andrew says, one note, applications can choose a single-threaded event loop and get a programming paradigm equivalent to Node.js. Yeah, but libraries should handle the possibility of multi-threaded event loop and to make a compile error, or to make a compile error if built-in single-threaded is, well, I would say it's different than true. Have actor models been explored in Zig? Oh yeah, Andrew answered. Oh no, Andrew did not answer. Let's see. Nectar says, I've seen some whispers, but I'm not exactly sure what the status of the conversation currently is. I think there are some. There is some code maybe in the standard library. I'm actually not even sure, but I think I wouldn't worry about this because all this stuff is perfectly implementable. Maybe the only issue that I would see there is, I think there are two issues. One is a practical one where maybe in other languages, if actor models are like hard coded into the language, you can enforce people, like you can force people to use them in a certain way, while maybe in Zig you would leave it to the user to make proper use of the API, and they could accidentally break away from it. This is a super general statement. I'm not even sure that's true, but that's one thing that might happen. And the second point I think is that actor models, I guess, are nice for correctness and ease of use sometimes. Kind of like Go with coroutines and channels are basically a poor man's actor model. I don't know. I think of it. I think what Go provides you as a poor man's actor model because I'm comparing it to what like Erlang offers. So it's what Go gives you is much less fancy. Even though I honestly like it, so no complaints there. So something like this is certainly doable. I would say that the philosophical problem there is that, well, if you want to make things efficient, you probably should not constrain yourself to a model like that. You probably want to try and squeeze in weird control flow, weird, quote unquote, weird control flow things, at least weird compared to the what the actor model offers you. So I think it would make total sense for that to be a library somewhere. It would totally be implementable. Oh, there is a library, Drone Wings Saville. Okay, interesting. So I haven't really found. So Kumari says I haven't really found something I want to implement that would need async await yet. So I haven't really played with it. Yeah. I think that really the entry point for this stuff, no joke, is client libraries. Client libraries are, I think, like the perfect scope for getting started because it keeps you on the async await API level. It doesn't force you to get into suspend resume. Or I should like the asterisk there is that like the small lie in what I'm saying is that it doesn't force you to go into the suspend resume layer as long as you're using the APIs in the standard library. More specifically, well, you clearly would use the APIs in the standard library. Well, I don't know, not clear, but you would normally use the APIs in the standard library when it comes to networking, for example. That makes sense. But for example, for my Redis client, at one point I needed a locking mechanism that would work well with async await, and that would also maintain ordering between different threads asking and queuing themselves to get access to a lock. I needed that ordering to exist because unordered access to the lock would cause all kinds of trouble with the architecture that I went with the client. So if that library wasn't available, then I would have needed to write it, and that kind of requires to use suspend and resume. But the library is there. So to my understanding, you can write a reasonably functional, full-fledged kind of application, kind of like I did for Redis. Pick your poison, find a database that you like, and start looking at how you can make it work both in blocking mode and in a sync await mode. And again, I assure you will find it's surprisingly easy. I should probably do a talk dedicated on that. I should probably explain how Redis is structured. It should probably be an interesting talk on two fronts. One on the front of how async await is integrated in it, and really the integration surface is so small because everywhere there's this automatic translation between normal calling convention and async calling convention, and the other half is I guess would be metaprogramming. So yeah, think about it. Like maybe you can write a MongoDB client for Zig. I'm not gonna do that. So somebody should. And please, for the love of God, don't let Mongo, what's the name of the company? Whatever. Don't let Mongo itself write the client because they are so bad at it. I don't even know where to begin. Anyway. So I don't know. Redis, I think if you want to, I'm biased. I like Redis, but if you want to try your hand at something that is simple to implement, not too like the query, the communication protocol is not too obtuse. It's nice to debug and everything else. Take your step at Redis. Maybe you can write your own client, and it's they're bad at writing servers too. Yeah, they are. Oh god. Oh my god. Don't get me started, man. The hardest part of working for Redis Labs was that I could not talk as much shit as I wanted about MongoDB. That was genuinely the hardest part. Anyway, a SQLite client. Oh, that's interesting. A SQLite client. The problem though is that SQLite it's not worked. So I have a use case for a LevelDB equivalent API. Nitro also said, did you go over the relationship between async await and suspend resume and why there's both? I didn't go precisely over the reason why, but I mentioned that these two groups of keywords are very, very different. If you are expecting asymmetry, so that somehow async relates to suspend and await relates to resume in a somewhat clean, abstract way, they don't. They do very different things, all of them. And as I said, also there is a bit of overlap. Like await kinda does some of the things that suspend resume await uses in a sense resume. So no, that's not even right to say. So in any way, what they do is a bit overlapped, and you need precise knowledge of what they actually do. You cannot reason about them in an abstract way. And what they do ties precisely into how continuations make the control flow in each thread jump in different points of the code. And here's the thing: you can see that already. Like I think Andrew gave plenty of examples of how this control flow manipulation works. in videos and also in the documentation, the standard library documentation, which, goddamn it, it's another thing that I forgot to mention in the list. Like in the docs, there's also some examples for these. The problem is, while they are perfectly clear, when I personally saw them, is you understand the example in isolation, but you still have trouble seeing the full dance, or at least that was for me. So my actual, like the question that I'll try to answer, that I need an answer to before preparing a talk on async await, is how to fill the gap. How can I bring people from understanding a example in isolation to understanding how this scales up to a full-fledged application? And as I said, the entire juggling, the entire dance keeps making sense. I'll get there. I suspect it's probably not too complicated. It's just a matter of properly identifying what the key parts of understanding are. And as I said, this is really, I think, tied to our, like, the zeitgeist of software engineering. Today, I think these things are not really stressed much in our education and in our professional life. And if they were stressed more, we would probably have less problems, or I guess different types of problems. But yeah, I'm thinking about this stuff constantly, so I'm sure I'll get to a, maybe not the perfect solution, but something that can help a few people at the very least. Spell resume is for bad boys. Yeah. Oh, another thing about a little Postgres client. Nice. Is it a gap that needs to be filled? Well, I think we would want people to. So, I think there are two answers. I would say yes, and I think there are even two separate yes to that question, at least from my point of view. One is, well, as part of my role, I think having more people be able to do more stuff with Zig is important for what I'm being paid for, and I guess in more general sense, I want personally people to write a good async stuff for me, so that I don't have to. But on the other hand, I would say if we don't do that, the result is the madness that you find in Python, for example. Like the way people implement a nice looking layer of async APIs for you in those ecosystems is crazy. The things that Python and JavaScript do behind the scenes is crazy. I know I'm being imprecise and hyperbolic, so it doesn't sound particularly well, but there are so many things, weird things that these languages do to hide the complexity from you. Like in JavaScript, I don't know why, but if you have a promise that results in another promise, await will unwrap all the promises. So await. So if the return type of a promise ends up being another promise, await will unpack both. While, for example, I was writing an API where there would be two precise moments. One where you want to await the code that produces the resulting promise, await that, obtain the promise, do some stuff, and then await the promise that you were given. But it couldn't work with JavaScript because await will unravel, like unpack, unfold. I don't know how you want to say it. Would flatten the entire promise functor structure. I don't know. And why is it doing that? I have no idea. It's janky. Everything is janky as fuck. So in Python, if you instantiate in Zig, if you do async function, the function runs immediately until it encounters a suspend point, which makes perfect sense. In Python, if you launch a coroutine without awaiting it, which is the equivalent of using the async keyword in Zig, in Python, the coroutine gets just instantiated as an object and it doesn't run. It doesn't do anything until you schedule it through await or a similar operator. And there are so many of these weird inconsistencies that then if you go and look into the implementation, you see that everything is glued together with like gum and a couple of nails and a bit of wood, and everything tries to kind of stays together as long as you don't stress it too hard. So I think there are a lot of downsides to having people like that status quo is what you get when people can't make the jump from understanding async await to understanding continuations. So I think if we want to make things better, we should try to aim for people to get there. Again, I'm saying this at the end of the day for completely selfish reasons. I don't want to deal with crappy stuff like that anymore. I would like for everything to be maybe not at the maximum efficiency like Proti likes, but I would like stuff not to be janky at the very least. So yeah. I can tell you that when I started implementing slightly serious async stuff in Python and JavaScript, and I mentioned JavaScript earlier, but like Python is so much worse at this than JavaScript. Like the APIs are all over the place. So Nectar says Go is a better model there, right? One of its main things is people complimented on its async model. I would say that Go is better in the sense that it's more it forces you to do fewer things, and so people don't do weird things. But Go is not. But Go is strictly. I would say the Go is strictly less efficient. Like using channels and Go and Go routines is strictly less efficient than what you can do with async await, because async await is a superset of what Go does. So I would say that in the best choice, like the best world, would be to have people make proper use of async await. And occasionally, when you're writing software as a user, you might want to opt into a simplified API that maybe you are more familiar with to make your application work and not worry about weird bugs. But that said, Go is inherently... Go is not the optimal choice. Go is a good choice if you want to make sure that you don't if you want to, I guess, prototype your application. If you are familiar with that API and you're comfortable with it, you can use it. That's my point. But it's not something that we should, I think, aim for when it comes to writing like actual libraries. Actual libraries should use async await and make full use of the proper async APIs, using suspend, resume, and smart ways of locking and not locking stuff. And Proti has a lot to say in that regard, so I'm looking forward to his talk. We should be next showtime, but we haven't finalized it yet. So let me read a couple of comments. Oh yeah, I was only referring in comparison to your JS Python example. Yeah, no, I agree. Compared to I don't know, honestly. So I would agree 100% with Python. Python is a mess. There is a library called Trio, which I think brings some sanity there, but it brings some sanity from a API perspective. I haven't inspected the implementation, so I cannot comment on that. But let me rephrase this. Let me put it this way: from a productivity point of view, and as the end user that ends up having to deal with the resulting software that the world produces, in my opinion, Go is vastly better than Python when it comes to async await. Compared to JavaScript, I'm not sure, because JavaScript, I think, while it's not perfect, has a much, much saner ecosystem culture around async stuff. While, for example, I found annoying the thing that await unwraps everything, I think you like every time I had to write something that had to do async stuff in JavaScript, it tended to be much more straightforward than Python, because JavaScript has pipes, everything tends at worst to accept a callback. So yeah, that said, I don't know. I personally like Go, so I tend to be very positive of Go. But I have to admit that I think JavaScript is probably not that bad. at least in my experience. So let me read a few other comments. Zig's Sun Library async event is equivalent to a concurrency, async await, I guess, is equivalent in a concurrency sense to how Go runtime works. The differences are only in memory management, the ability for async functions to return values. For example, we can implement Go channels in userland in Zig. Oh yeah. I have a lot to see Go's async style done in Zig, mostly because I don't know much about the underlying implementation for Go. We don't have select implemented yet though. It's an accepted proposal, yeah. So yeah, we need select. And since Matt says also, and since I work with Go devs, that would help talk Zig async versus Go async. Oh yeah. Proti points also out that there's some examples of Zig in the Zap repo. It already has channels where groups go, and recently with Lithu's help IO. Oh, yeah, nice. Oh yeah, that's. I don't know, King. Are you going to present about Zigo in your next talk? Go rid of color. Go got rid of color entirely. I think Nectar, if you haven't watched the Redis Conf talk, I think you can give it a look. I think Andrew answers some of that. Yeah, you can always go something, and that's it. The problem is that if something was supposed to return a value, now you have to synchronize with the channel, and that kind of ties you into a model where you don't always like you don't always not always everything looks as good as it should, and I guess works as efficiently as it should when you have to chuck a channel in the middle every single time. And I think you can do better with async await when it's used the right way. Okay, Proti wants to talk about schedules in general. Okay. 190 YouTube subs to partnership. Yes. Thank you also. Me and my other accounts. Yeah. I'm so close. I really want to get this freaking partnership because Google, I mean, I don't know what's up with the world right now. 2020 and it's not gonna be over after 2020, but I don't know. Google now wants to add ads to everything. At least they could do the decency of paying for some of the t-shirts that I have to send to speakers, for example. I think we can do exclamation point YouTube. They do a good job with the bot. Yes. So yeah, there's also that. Well, in any case, I think that async await is a very, very interesting topic, and we should talk about it more in the future and from different angles. And we need more applications to use that. And I think that once we start showing how we can be faster and more efficient than quote unquote the competition, people will be more interested in doing the stuff in Zig. We get more libraries with more stuff, and everybody is happier. I mean, if you are here for the 0.70 release party, I don't know why I said 0.70. That shows you that when non-native speakers learn English, they learn a mix of everything, and anyway. But in that Showtime episode, King Proti from the chat demoed his own scheduler and compared it with an equivalent implementation in Go and Rust, and the Zig implementation was pretty damn fast compared to the other two. So there's space for a lot of interesting things to happen there. So I'm also looking forward to writing spicy blog posts in that regard. So yeah. I think that's it. I don't have any spoiler for next Showtime in terms of what I'm going to do. As I said earlier, we are trying. Let's see if we can organize some kind of fireside chat, roundtable, group talk around what's going on with Apple Silicon, since it's a very relevant topic now, and we are spending a lot of effort trying to make things better there. And Proti should be doing his talk on schedulers. So I think it's going to be another good episode. Thank you everyone for being here and watching. I guess we can call it a day. Bye bye.